Let's start talking about OSPF quiz questions now. So we have around 22 I think questions. So I will go through one by one. I will read and explain. So this is important. We will verify our knowledge, what we have learned so far, okay? So let's start. First question, how many routers can be placed in any given OSPF area? So 50, 100, 250, less than 50, it depends. So you might think now, if you read old Cisco documents, maybe 40, 50, you will say 50, but no. Answer, almost in any network design question, any network design, basically when you talk with the customer as well, it depends. Depends on many things actually here, okay? It's not 50. Even in the old days, you cannot say 50. It was wrong. Why? Because one company's equipment might be much better than other older devices, less CPU, less memory resources maybe they had. Here today, even modern network devices maybe can handle much more devices compared to 10 years old devices, but still depends on the hardware, so device, CPU, memory, depends on the network topology. If it's full mesh, each and every router connected to others, right? So if it is hub and spoke, just we have spoke connected to hubs. If it is ring, every router is connected to two other routers. So it depends on the topology, it depends on the number of devices in the network and the stability of the circuit, stability of the links between the devices, the hardware of the devices. That's why it depends. Also, as you can see the answer, by the way, for each question I am sharing the answer. You can read if you want later on, but why? Device, CPU, memory, so hardware, the topology in your network, if it is full mesh, if it is partial mesh, so the number of links will grow. It depends on also other things like stability of the links in your network, okay? So that's the important question. So question 2. Why many different type of LSA are used in OSPF? Choose all that apply. So I am doing this one in purpose, so choose all that apply. I could say choose 2, choose 3. Right now you don't know how many of them you should choose, but let's discuss the options, okay? Provide scalability, allow multi-array OSPF design, provide fast convergence, provide high availability and better traffic engineering. By the way, traffic engineering can be done with the layer 2, we talked in the layer 2 design, and with the layer 3 via IGP protocol, OSPF, ISA, CIGIP, RIP. It can be done with BGP as well. We will talk in BGP lesson. Also, nowadays, of course, famous, probably you are following segment routing TE, SRTE, but RSVP-based traffic engineering, of course, has been around for decades. So here, it's not for traffic engineering. LSAs, number of LSA, we have 11 type of LSAs in OSPF, we talked during the session. So we are using for scalability. Why? If we don't have multi-area OSPF design, if we have just single area OSPF, backbone area OSPF, then we can only have type 1 and type 2 LSA. Okay? If each and every link is point-to-point link, then we will have only type 1 LSA, but interface type may be Ethernet, so you need to say OSPF network type is point-to-point, otherwise there will be DR election, there will be type 2 LSA. But maximum type 1, type 2 LSAs, of course, if there is redistribution, there might be type 5 LSA as well for the external destinations. Other than that, normally you don't have type 3 LSA, you don't have type 4 LSA in just single array OSPF design. So why we have? Because we want to have multi-array OSPF design. Why? For scalability. We talked about OSPF scalability during the session. So for scalability, one of the approach for scalability is multi-array OSPF design. We talked about the other things for the OSPF scalability. One approach was multi-array OSPF design, and it can be done with the different type of LSAs. That's why answer here, provide scalability and allow multi-array OSPF design. So we want to have multi-array OSPF design. Why? Because it provides scalability. That's why two of them here the correct answers. Question 3. What does topology information mean in OSPF? We talked about it. We have two different information, reachability information and topology information. What is topology information question is asking. So it says IP address of the directly connected interface. No. Topology mean which router is connected to which other. So the SPF, shortest path first algorithm, basically can use this information to create a graph for us. IP address of the loopback interface, no, not the IP address. These are reachability information. Option C provides an IP reachability information and the metric of all the physical and logical interface. Again, here is talking reachability information. The metric and the IP address. Option D provides a graph of the OSPF network by advertising connection information such as which router is connected to which one and the metric of these connections. So option D is the correct answer. Topology information, router A is connected to router B and router B is connected to C. Now each and every router knows this information, and whichever the subnet coming from router C, router A knows this as well. And each and every router in the same area knows exactly the same topology information. Question 4. Why more than one area is used in OSPF network? Again, we need to look for the scalability. One of the options should be around scalability, because more than one area, single area would be enough. And we don't have numbers. We cannot say it. The question one was asking how many routers we can place in one OSPF area, and we said it depends. So, but once you have, especially, what is then the requirement? What is the decision point having more than one area, right? So in real life, things are a little bit different. Like people, when they have so many branch offices, let's say, okay? So they group some of those branch offices per country, per region, etc., or per interface speed. Okay, like they can say 10 megabit interfaces between hub and spoke network, then all these 10 MB spoke sites will be in area 10, something like that. But other than that, router LSA, type 1 LSA, this type 1 LSA size of the area shouldn't exceed interface MTU, which generally comes as 1500. So if it exists, if it's bigger than interface MTU, then there will be fragmentation. In OSPF version 2, so in IPv4, the routers can fragment the packet. So, but fragmentation is not a good thing. It is, again, resource intensive. That's why we want to avoid fragmentation, right? So then here, why more than one area is used in OSPF network? Answer should be around the scalability. Let's have a look at the options. Option A, they are used for high availability now. Not more than one area for high availability. It is not like one router, let's say a single router is connected one interface to backbone area, another interface to non-backbone area. There is this design anyway wouldn't work. Option B, they are used for easier troubleshooting. No, more area, basically backbone, non-backbones, etc., makes troubleshooting a little bit harder anyway. So especially when you send a summarization from the backbone to non-backbone, non-backbone to backbone, etc., or all this operation basically, you need to configure more things, access list, prefix list, then tie this access and prefix list into the route map and apply this route map to interface or routing process. Lots of configuration comes and it creates complexity, so it's not easier troubleshooting. Option C, they are used to provide scalability by having smaller flooding domain. Flooding domain mean now single router, if you add interface or if there is any link failure, device failure, this information will be sent, will be flooded to the area, but not to another area. So if something happens in area 0, then the router in area 10 will not know this, who failed, okay? Now, what is the topology, new topology? This topology information will not be sent between the areas. We talked about this during the session. So answer is option C. What option D says? Since topology information is not shared between OSPF areas, they provide better security. No, this is done for scalability. This is done to keep the basically less amount of information in single area, not for security. Question 5. Which router in the below topology should be an ABR, area border router? Let's have a look at this topology. At the left side we have full mesh, at the right side also we have full mesh, then router G and router H basically connecting these two physical full mesh domains to each other. So answer, if you will have here multi-area design, router G and H should be ABR, guys, okay? Why? Because when they are ABR now, all the other routers at the left and right can be in different area. Let's say left full mesh domain can be in area 10, another right full mesh domain can be area 20. G and H, like an hub and spoke now you are creating, and router G and H will be your two hub routers and area 0 between them, backbone area, and all the other routers in these full mesh domains will be in their respectively individual areas, okay? Area 10 and area 20. Out of this, G or H, actually it would be nice to have here G and H, so option A is the answer for this question, okay? So question 6. In the below topology, router B needs to be reloaded. Network operator doesn't want any traffic loss during and after router B's maintenance operation. Which OSPF capability should be enabled on the router B? Let's have a look at what we have here. We have four routers A, B, C, D, okay? And router A and D at the edge, they are BGP route reflector client. BGP is running as well, okay? OSPF and BGP. And router B and C is route reflectors, okay? So inline route reflector we call it, so they are in the data path. So if we would have MPLS here, by the way, router B and C doesn't have to run BGP. This concept is called BGP free core. In BGP session we will talk about. Now here we don't have MPLS, we don't have any tunneling mechanism. If we would have GRE, by the way, still router B and C wouldn't need to run BGP. But we don't have MPLS, we don't have GRE, nothing. Just we have IGP and BGP. So in this case, what happens? We are running OSPF, we are running BGP. Router B we will take it down, and what happens if we do it just without signaling, without informing other neighbors? Basically, we will see packet loss. So in each routing protocol, in each IGP, as well as in BGP, we have a capability to signal other routers that we are going down. We will be going down, and in fact, not only going down. When this router B goes down and comes up, and if it tries to take the traffic right away, immediately, there will be still packet loss. Let me explain why. Router B and C in the data path depends on basically the traffic flow, because it could be ECMP, equal cost multipath. So if traffic source is router A, destination is router D, from router A to D traffic, if there is an ECMP, half of it will go to router B and half of it will go to router C. We assume there is 50-50 hashing on router A is done. Not all the time, depends on the flow. Some flows might be mice flow, some flows might be elephant flow. So, but let's not go into details, just ECMP we have, let's assume. So router B, if goes down without signaling, without informing other IGP neighbor here, which is router A and D, we will see packet loss. So that's why in OSPF we have a feature, we have capability called maximum metric router LSA. With this, router B will announce basically in its router LSA, type 1 LSA, maximum metric, which means from the SPF point of view, it will not be taken into an account anymore. Router A, for the destination, BGP-based destination, who is the next stop? Router D. BGP-based destination, BGP next stop, router D, but there will be recursive lookup. So router A needs to know who is IGP next hop, which is router C in this case. Router B will not be taken into an account because we set maximum metric router LSA on router B. Okay. So far so good. Router B after this maximum metric router LSA configuration can be taken down. But I told you, let's say you finish the operation and now immediately you want to take the router B in the network. Now router B will take the traffic, network traffic. If IGP converge faster than BGP, and this is always the case anyway, right? So first IGP converge, and after that BGP converge. But here, IGP-wise, IGP point of view, router B shouldn't advertise with the regular metric, but it should continue to advertise even after maintenance operation. It should continue to advertise with the maximum metric. Okay, router B should advertise all the prefixes with the maximum metric. So after BGP convergence finish, router B should start advertising with the regular metric, then still we can have equal cost multipath ECMP. I call it IGP-BGP synchronization. There is nothing like this normally. We have special feature called IGP-LDP synchronization. And in any ISP network, I see this one anyway. But IGP-BGP interaction, you can call it. Synchronization, you can call it. Idea is IGP shouldn't take the traffic immediately. It should wait BGP to converge as well. Okay? So how BGP will make sure the convergence finished? There is BGP end of rip marker. So when this basically packet is seen within the BGP update message, so routers understand that there is now convergence finished from the BGP point of view, and BGP will signal IGP to advertise regular metric. So the answer of this question, it was a little bit long explanation, but answer is option A, which is maximum metric router LSA on startup wait for BGP. This on startup wait for BGP, here OSPF is waiting BGP on startup when you finish the maintenance operation and take the router B now into an account. So router B is connected to network anyway, and now router B comes up, line card comes up, but router B IGP will converge as well, but will not advertise regular metric because router B is running BGP as well, and D is sending all the prefixes to router B, and once router D delta finish its job, it will send end of rip marker to router B. Router B BGP process knows that convergence is done on the BGP level, and it will trigger IGP to send, advertise regular metric. So then router A from the IGP next hop point of view can take router B into an account as well, and it can do ECMP. Question 7. How many levels in OSPF hierarchy used? How many levels of hierarchy we have, guys, in OSPF? 1, 2, 3, as many as possible. Yes, answer is 2. Why 2? Why 2? Because we have backbone area and we have non-backbone areas. So we have backbone areas and non-backbone areas, and non-backbone areas cannot be connected to each other directly. All the non-backbone areas should be connected to backbone area, and the prefixes from, let's say, area 20 needs to go to area 0 and then should come back to area 10, let's say routers, okay? Area 10, 0, 20, these area 10 and 20 can communicate via area 0. So that's why we call it 2 level of hierarchy, backbone area and non-backbone areas, okay? In ISAS, the same, maximum 2 level of hierarchy we can have. But in EIGRP different, we will talk this one in EIGRP. Which below options are correct for OSPF ABR? So choose all that apply again. I didn't say choose 2, choose 3. So let's have a look at which ones are correct, okay? It might be all. It might be just 4 of them. Let's see. It slows down the convergence. Yes. If we have ABR, it slows down the convergence. How much slowness it brings, we don't know exactly. We cannot say this amount, but extra some amount. Imagine if you would have just single area, backbone area design, Now you have ABR, you have backbone and non-backbone areas. This ABR job converting some LSA into another LSA like type 1, type 2 of area 0. They will not be sent as type 1, type 2 now, but they will be summarized into type 3 and will be sent to non-backbone area. Or if you have, let's say, type 5 LSA, then when there is type 5 LSA sent into the area 0, ABR job for the non-backbone area is what? ABR will see this ASBR through the type 1 LSA and convert this type 1 LSA into type 4 LSA and send it to non-backbone area as type 4 LSA. All this conversion, etc. basically takes time. It slows down the conversions, guys. Option A is correct, by the way. Another one, it generates type 4 LSA in multi-area OSPF design. Just I explained type 4 LSA. Yes, ABR basically generates it by looking the type 1 LSA of the ASBR, and it sends type 4 LSA in other areas. Why? For the ASBR reachability. Okay. It does translation between type 7 to type 5. So yes, it does translation between, of course, type 7 to 5 if we have an SSA area, of course. If we have an SSA area, all the redistributed prefixes will be seen as type 7. And this type 7 will be converted by we call it NSSA ABR. NSSA ABR into the other areas as type 5. Okay, so C correct as well. So far A, B, C are the correct ones. D, it does translation between type 5 to type 7 in NSSA area. Guys, there is no type 5 to type 7 translation. This is wrong, okay? Technically wrong answer. Option E, it prevents topology information between OSPF areas. ABR, exactly. There is no topology information between the areas. Topology information is known up to the ABR. After ABR, into another area, no topology information. Only reachability. So in area 10 routers, any of those internal area 10 routers, they don't know what is the topology, who is connected to who, what is the metric between them in another area. So we talked about that. That's why it prevents topology information between OSPF areas. ABR is doing a lot of things, right? So answer is A, B, C, not D and E, okay? Why designated router is used in OSPF network? So let's have a look at the options. It is used to have an ABR in the network. No, you don't have to have multi-area OSPF design. Even in the single just backbone area, you can have DR, designated routers. It is used to create topology information. You cannot prevent topology information in OSPF anyway. So even if you have multi-area OSPF design, up to ABR we have this topology information. ABR just stop and don't send the topology information between the areas, but you still have inside each and every area, for that area, topology information on each and every router. That's why option B is wrong as well. Next slide. Yok, geri gel tekrar ya. Questions 9'un olduğu slide'a. C, it is used to centralize the database instead of keeping distributed OSPF linked state database in every node. No. So, unless you don't have controllers, okay, but even in that case, you will still have distributed OSPF database. So each and every router inside the same area, they will know exactly the same topology information anyway. But if you have centralized controllers, even if you have multi-area OSPF design, this controller can receive the topology information from each and every area. That's why it can create end-to-end optimal path. Normally, multi-area OSPF design without the centralized controller, you cannot have basically inter-area optimal routing. You cannot guarantee this, okay? But the centralized controller, centralized node can get from each and every ABR in your network and can provide end-to-end optimal path with the given constraint. Even given constraint, we will see in our SVPTE, traffic engineering, end-to-end optimal path, okay? Whatever your constraint is, whatever the optimality for you, it can be the lowest bandwidth, lowest latency, or maybe highest bandwidth, highest latency, depends on the application anyway. So which mean option C is wrong as well. So D is correct one. It is used to avoid flooding information between each device in multi-access network. So if it's Ethernet, if you have 10 routers connected to Ethernet segment, basically instead of having 10 routers, like 50 OSPF neighborship, all these routers just will have neighborship. 8 routers will have just neighborship with DR and BDR. Those remaining 8 routers will not have basically OSPF neighborship. If something happens, if you add new interface, remove new interface, if there is failure, etc., this information will not be sent each and every router separately. Instead of receiving 10 update, you will receive update from DR now, and basically it gives, of course, scalability for us. Question 10. Which below feature is used to avoid black holing when OSPF and LDP are used together? So OSPF, IGP, LDP for MPLS labels, for the transport label I am talking about. LDP can be used for service label as well. We will talk all these details in MPLS, but let's have a look at OSPF, so IGP and LDP. Okay, OSPF fast reroute, no. OSPF fast reroute can be done with the mini IP fast reroute mechanism. LFA could be one, okay, loop-free alternate. When there is remote LFA, LDP might be required, but remote LFA is not only the option for the OSPF fast reroute anyway. We have MRT, maximal redundant 3 FRR. We have other academic approaches for IP FRR mechanism like U-turn alternate, not via. Those are not implemented by the vendors, but we have other mechanisms as well. So remote LFA might require LDP because vendor implementation requires it, but it could be GRE tunnel, on-demand GRE tunnel as well. So OSPF fast reroute doesn't require LDP. OSPF multi-area design, of course not. You can have just single IGP without any MPLS, single IGP through multi-area OSPF, or it could be ISAS and multi-level ISAS. You wouldn't need LDP anyway. IGP LDP synchronization, yes. With the IGP LDP synchronization, basically when there is, if you want to take one node down, if you want to do maintenance, let's say, basically this router needs to signal each and every router that I am going down, and if you are running on the same router, different interfaces of the same router, LDP as well, when there is a failure, nothing happens, so everything goes well. But when that failed device or maintenance you are doing, let's say, when you bring it down, everything goes well. But when you bring it up, things can be weird, right? Why? IGP converge faster than LDP, okay? LDP requires this. IGP converge faster than LDP, but what we want, exactly what we did with the IGP BGP synchronization, IGP should wait LDP, otherwise there will be black holing. Because why? You are receiving the intermediate nodes down, you will take it down, and basically this is intermediate node, traffic is passing through that node, and when you take it down and put it back, IGP, if IGP takes the traffic, but there is no LDP assigned label yet, but that router is expecting label for swapping, because forwarding is not based on IP, but MPLS, and without MPLS label binding, traffic will be black holed. That's why IGP should wait LDP to finalize its job, all the label for all the routing table entry, then IGP should signal, okay, I am ready to take the traffic. We call it IGP LDP synchronization. It is done on any service provider network if they use IGP and LDP. Nowadays, I am seeing more and more segment routing deployments, and if you have segment routing, we will talk later on in MPLS, you don't need this IGP LDP synchronization issue or concern, let's say, because you don't have separate label distribution protocol when you have segment routing, okay? Because all these MPLS label, we call them SID, segment identifier. This MPLS label with segment routing will be sent within the IGP update. With OSPF, OPOC LSAs will be used for this, okay? That's why you don't have two different protocols, one for IGP, one for MPLS label distribution, you have single protocol, which is IGP, Interior Gateway Protocol. That's why you don't have this IGP LDP synchronization problem. That is the whole idea behind it. Segment routing basically removes this IGP LDP synchronization, but if the question is saying, if we will have OSPF and LDP, then we will need this IGP LDP synchronization feature. D is saying converging OSPF faster than LDP in case of failure. Yes, it can, but what is the feature we need for this IGP LDP synchronization? Okay. Question 11. Which below option is correct for the given topology? Okay. So in this topology we have backbone area, area 10, 20 and 30 is connected. Also EIGRP is connected to area 30, guys. So let's look at the options, and now a couple more questions will come after this, and still we will use the same topology but different basically area, and we will have different questions for those areas. Let's have a look at this question first. So same topology. Area 20 has to be stub area. No, right? Sorry, there is nothing to basically prevent area 20 to be regular area. Doesn't have to be stub area here. Sending default route might create suboptimal routing for internal area 20 routers. Have a look at the topology. We have only one big ABR here, right? So ABR is connecting area 20 to the backbone area, only single router. So we can have, when we send the summarization, so when we have summary route, let's say we have /20s, 24s, /32s, whatever, and we are sending /16. If we have two ABR, we might create suboptimal routing. Why? Instead of sending, let's say from left router, we are sending from right router. So maybe the optimal path, if we would send through the left ABR, would be the optimal path, but we are maybe sending to the right one. Why? Because maybe two ABR is sending with the same metric, so we can do ECMP, half of the traffic will be suboptimal. You got my point? So, but here we have single router, single ABR connecting area 20 to the backbone area, so we don't have this problem anyway if we send default route. So see, ABR of area 20 has to be designated router. No, I mean, there is no restriction. ABR or any other router can be DR, designated router. But D is saying area 20 doesn't receive type 1 and type 2 LSA from the other area. What we said, if we have multi-area design, we will not receive type 1 and type 2 from any other area into our area. So that is important. This information will be sent, type 1, type 2 will be summarized without sending any topology information with the type 3 LSA into the other area. So reachability, yes, but no topology, no type 1, type 2 between the areas. That's very important. So answer is option D. So let's have a look at this question. In the below topology, area 30 is an NSSA area, which below option is true. So 30, if it's NSSA, which below option is true? A is saying there will not be any type 3 LSA in area 30. No, there can be. Why? Because it is NSSA area. In NSSA, from the other areas, we can have type 3 LSA. If it's totally NSSA, no type 3, but it's just saying NSSA. So option is wrong. ABR of area 30 will translate type 7 LSA to type 5 LSA. So ABR of area 30 will translate 7 to 5. Yes. Will there be any 7? Yes, because we have EIGRP connected to area 30, which is NSSA. Those EIGRP prefixes will be seen as type 7 inside the area 30, which is NSSA. And this ABR will basically translate 7 to 5 and send into the old network as type 7, sorry, type 5, 7 to 5 translation, and 5 in the other places, but inside area 30, those prefixes as type 7. And let's have a look at just the C and D. They should be wrong anyway. There will not be any type 1 or type 2 LSA in area 30. There will be, of course, internal routers. Their type 1 LSA has to be there all the time. There can be type 2. We don't know that. If there is multi-access network like Ethernet, there will be type 2 as well. But each and every router has to create type 1 LSA, router LSA, we know that. And option D, EIGRP prefixes will not be allowed in area 30. It will be. Redistribution is allowed in NSSA area, and those EIGRP prefixes will be seen as type 7. Okay. Question 13. So in the below topology, area 10 is totally NSSA. Which below option is true? Area 10, totally NSSA. Now this time, totally NSSA. Let's have a look at. Area 10 will not have any type 1 or type 2. No, internal routers, their type 1 and type 2 will be there. It's wrong. Area 10 will not have EIGRP prefixes. Yes. They will not have EIGRP prefixes if it is totally NSSA. Why? Normally, EIGRP prefixes into area 30 will be seen as type 7. And then ABR will basically, ABR of area 30 will translate 7, so EIGRP prefixes into type 5 and will send everywhere. But what we said, area 10 is totally NSSA, which means there is no 5, type 5 LSA, there is no 4, there is no 3. So EIGRP prefixes will not be seen. B is correct. Let's have a look at the C and D as well. Area 10 cannot reach EIGRP prefixes. No, it can. If you have total NSSA anyway, you need to have default route, and through default route you can reach to any other, basically, prefixes, any other routing information in the network. And D, both ABR of area 10, okay, we have two ABRs, will do the type 7 to 5 translation. No, let me explain this. Area 10 is total NSSA, right? Let's say we are redistributing, we are connecting EIGRP or BGP or any other routing protocol, or even, let's say, different OSPF process, and we are redistributing in this case from the external routing to the area 10. And these ABRs, normally NSSA ABR job is 7 to 5 translation. But once we have more than one ABR, only the lowest router ID will do the translation. So we have two ABRs, they will do the election. Who will do the translation? Whoever has the lowest router ID, it will do the translation and send it 7 to 5, so type 5 LSA, into the network, okay? Just one router will send, not both of them. That's why D is wrong as well. Answer is B. Question 14. In which below topology OSPF is worse than EIGRP in large-scale implementation? Large-scale OSPF, so full mesh, partial mesh, hub and spoke, and ring. Very technical question, in fact, and we need to know a lot of features of routing protocol on top of different physical topologies. So let me explain. So answer is hub and spoke, but we need to know some advantages and disadvantages of routing protocol or on any given physical topology. So ring is anyway very hard for any topology, okay? It is the, yes, cheapest physical topology which provides redundancy, which is a good thing, and any features like IPFS, reroute mechanism, etc., OSPF, EIGRP, ISAS suffers on ring topology. And here question says large-scale design, large-scale design, OSPF worse, right? EIGRP, for example, on hub and spoke network is, we consider, best, okay? And OSPF is worst. We need to know this one, and the point is OSPF can work, of course, but in large-scale design, we need to tune a lot of parameters of OSPF to basically to run on top of hub and spoke network. On the other side, EIGRP is designed for this kind of hub and spoke topologies, and there are some features like EIGRP stop to run in a large-scale hub and spoke network and preventing the spoke routers to be transit routers. We will see this one in EIGRP, maybe for this question a little bit early, but I maybe would forget that OSPF in a large scale hub and spoke would be the worst. That's why I wanted to share here. Hub and spoke, EIGRP or BGP is still good. For BGP, again, we need to we need to tune a lot of things. Let me just give an example. Again, to prevent spoke router to be a transit router in case of failure, let's say we have two hub routers. One hub router, if they use to reach to the another hub router via spoke router, that spoke router becomes transit routers, right? In the transit path, it would be used. So in many cases, we want to avoid this. In BGP, we have anyway ASPF loop prevention. In EIGRP, we have EIGRP stop. In OSPF, maximum metric router LSA can be used, but we have other mechanisms we need to implement for OSPF to work. And large-scale OSPF, worst thing, in the hub and spoke physical topologies, guys. We need to, depends on the connections, we need to have virtual link, or we need to have RFC 5185, so multi-array OSPF adjacency, so in order to prevent suboptimal routing, so on and so forth. I don't have topology right now to show you, but again, transit path or having multi-array OSPF adjacency, we need to tune many things. That's why configuration becomes more complex, managing and troubleshooting becomes more complex when we have large-scale hub and spoke network and OSPF routing protocol on top of that. Why OSPF is used as an infrastructure IGP in an MPLS VPN environment? Why OSPF as an infrastructure IGP? What is infrastructure IGP? In MPLS VPN network, especially with the service provider, we have IGP for the general routing, routing table. Also, when MPLS VPN is provided by the service provider to the customer routing is placed in the VRF. And we have routing protocol towards customer in MPLS layer 3 VPN especially, right? Towards customer routing protocol, also internal ISP MPLS network of the service provider, we have also routing protocol. And the question is asking, why then we have that routing protocol, right? Inside the ISP network, inside the service provider, let's say, network, when they have MPLS VPN. So let's have a look at the options. To carry customer prefixes. No customer prefixes. If we have MPLS layer 3 VPN, towards the customer, we can have as a PEC routing protocol, any routing protocol. It can be static routing, it can be OSPF, RIP, ISAS, even ISAS, I'll show you, EIGRP, all of them, right? But customer prefixes between the edge routers of the service provider, edge routers in MPLS network is carried via multi-protocol BGP. So VPN address family we will talk about. Customer prefixes is not carried the infrastructure IGP, the IGP protocol, whatever it is, OSPF or ASAS is used in MPLS VPN network. But if it's enterprise, EIGRP could be used as well. We will talk about it. But customer prefixes with the BGP, okay? Reachability between the MPLS VPN endpoints. Yes, these endpoints in MPLS VPN is we call PE routers, okay? P router in the middle, there is another functionality of it. Okay, we will talk in MPLS, but endpoints reachability. So PE routers needs to reach each other, and on top of that, when they reach each other, we can have BGP session and different services like layer 2 VPN with the Martini. I will explain that. We have targeted LDP session. So we have all the intelligence anyway at the edges. Okay, and here IGP in OSPF or ASAS as an infrastructure IGP is used to connect those endpoints, okay, MPLS VPN endpoints. That's the correct answer. So C, OSPF is not used in MPLS VPN environment as an infrastructure IGP, but BGP is used, no, okay. BGP is used for service, not to connect these two endpoints. We need to connect those two endpoints. And then on top of that, BGP is used to advertise customer information, which we call service. Okay, layer 2, layer 3 service. And option D says LDP requires OSPF as an IGP now. Okay, LDP, it could be again EIGRP, ISAS, static routing. Okay, not BGP. LDP cannot assign a label if the prefix is learned via BGP, because BGP also can assign a label which we call what? BGP plus label, RFC 3107, now newly updated and obsoleted by RFC 8277 and so on and so forth, but LDP doesn't require OSPF as an IGP. It can be any other interior gateway protocol. Static routing is interior gateway protocol as well, right? We know that. Which OSPF feature in MPLS VPN PEC is used to ensure MPLS service is always chosen as primary link? Yes, many of you now know probably the answer. Yes, it is sham link, but a little bit let's talk about it, right? So when we have MPLS VPN, let's say customer side, 2CE and MPLS network, CEs are connected to MPLS VPN, but you connected backdoor link we call, okay, backdoor link. So between CEs, non-MPLS VPN, and you are running OSPF there, and everywhere area 0. Everywhere area 0. So backdoor link area 0, and then CE connection to the PE area 0 to the MPLS VPN, okay, area 0. Now the prefixes also in area 0, you advertise from CE, let's say right CE side to left CE side. The prefixes left CE we'll see as type 1 LSA, but from the MPLS VPN backbone, prefixes can come via type 5 or type 3 without sham link. I will not go into all the details, but with sham link, prefixes from PE side can come as type 1 LSA. So CE can learn from the MPLS network the prefixes, let's say CE2 is advertising the MPLS VPN side, then via multi-protocol BGP, PE2 is advertising to the PE1, PE1 is advertising to CE1. In the MPLS VPN network, you run sham link, okay, between the PE devices, OSPF sham link, and this sham link will give ability from PE1 to send those CE2 prefixes as type 1 LSA to the CE1 side. So now CE1 received the same prefix from the MPLS VPN network type 1 LSA, from the backdoor type 1 LSA. Now with the metric manipulation, CE1 can choose MPLS VPN domain, MPLS VPN network as the primary path. So OSPF sham link is must if you want to ensure, okay? Or you need to play with the basically this backdoor link, non-backbone area, etc., etc., and other than that, if you want to ensure sham link is must, okay? Question 17, which below options are correct for OSPF? Choose all that apply. Again, I am saying, but it would be easier if I would say choose 2, choose 3, whatever, right? So you would know. Let's have a look at OSPF version 2 doesn't support IPv6, so when IPv6 is needed, OSPF version 3 is necessary. That's true. Okay, for the IPv6 support, we need OSPF version 3. But once we have OSPF version 3, we can support both IPv6 as well as IPv4 with OSPF version 3. With version 2, only IPv4. So option A is correct. OSPF virtual link shouldn't be used as a permanent solution as in OSPF design. Yes. Do you want to have like a GRE tunnel staying in your network all the time and mini GRE tunnel maybe? You don't want, right? So in pure design, simple design, always we want simple as possible. Keep it simple. Stupid. We call it what? KISS principle. I'm not saying you stupid. Don't get me wrong. So KISS principle, we will explain. Actually, I want to do separate video for KISS principle. It's not that simple, even the principle. Okay, simple. How we can make it simple, right? We will talk about it in a separate video. So we don't want virtual link to be stay there. So extra state information you are keeping anyway, and you are troubleshooting, but control plane is going this way, data plane can go in another way. With the virtual link, we don't want that. OSPF and BGP are the two separate protocols, so when OSPF cost changes, it doesn't affect BGP path selection. No, it can. Although we will see in BGP in very detail, but in BGP best path selection process, okay? If we are talking IBGP, guys, OSPF cost can affect everything. Why? Because maybe internal IBGP router is deciding the best exit point, the closest exit point by looking the IGP cost. Okay, we call it hot potato routing. I will explain it in a very detailed way. But OSPF cost change can affect the closest router selection. That's why, yes, they are two different protocols. Everybody knows that. But OSPF cost change can affect BGP selection. That's why once we do something in OSPF, we know that it will affect many other things in the network. Not only BGP, it can affect LDP, it can affect any other technologies in the network. That's why interaction is the most important thing that the designer should know. So in this case, OSPF and BGP, yes, they are different protocols, but best selection will be affected anyway if you are the internal IBGP speaking router deciding the closest exit, okay, if that IBGP speaking router has that luxury. Because if you have BGP route reflector, this internal speaking router, internal IBGP router will not even have two exit points, just one of them, and on BGP route reflector we need to play add path, we need to do shadow RR or BGP optimal route reflection. We will talk in BGP a lot, okay? But option C is wrong. OSPF can carry the label information in segment routing, so LDP wouldn't be necessary. That's true. In segment routing, the SID, segment identifier, or MPLS label, if we are doing with the MPLS data plane, is carried within the OPAC LSA in OSPF, okay? So we don't need LDP in that case. So when we have segment routing, we don't need for the transport label switch path, which means between the PE devices, the reachability, the tunnel, you can call it. We don't need LDP, we don't need RSVP, okay? So that's why option D is right as well. OSPF, unlike EIGRP, support MPLS traffic engineering with dynamic path calculation. Yes, that's true. Here, OSPF and ISAS actually, both, okay, unlike EIGRP. Dynamic path calculation, we have a mechanism called CSPF, constraint-based shortest path first algorithm. So CSPF can be used by only link state protocols, which are OSPF and SAS. We will talk in MPLS traffic engineering in detail, CSPF, how it works, what are the other constraint-based mechanism and pros and cons of each model. So so far, just what we should know, link state protocol, OSPF and both ISAS can basically support dynamically traffic engineering if some failure happens, or if we add extra capacity, basically OSPF and ISAS, because they know the topology information, CSPF can take into an account, now this LSP we can basically optimize it and we can signal it over this new path, etc. So all this dynamic path allocation, LSP creation or LSP movement can be done with the OSPF and ISAS, not with the EIGRP. What is the reason to place all routers in area 0 backbone area even at the beginning of OSPF design? So even if we are designing greenfield OSPF network, which means we don't have anything, we are now designing the network, and can we just place all our routers in, let's say, non-backbone area? Why people, if even, let's say, single area, if you will design and maybe after a couple years there is a growth, so lots of routers are added, new locations are added, maybe you will need later on multi-area OSPF design, but today you don't have that basic number of routers, and basically you will just create single area OSPF design. Can you place all the routers in non-backbone area, let's say area 10? Yes. Would it work exactly as placing all the routers in area 0 backbone area? Yes. Then why we are not placing all those routers, all of your routers in area 10? Why people are choosing area 0, or why we should choose, why we should enable in the beginning, if we have single area, just the area 0 on each and every router? Do you know options? But the answer is future. Let's say in the future you want to enable multi-area OSPF design. If today in the beginning, if you enable backbone area 0 on each and every router, future migration to the multi-area OSPF design will be easier. Why? You don't need to touch core routers, so backbone routers, but you can just touch edge routers, okay? You can convert area 0, the edge router link towards the core, towards the backbone. Those links only area 10, 20 non-backbone areas, and between the core routers, you will have just area 0. You don't need to touch them, and don't touch core router anyway, okay? Blast radius will be huge, which means if one router fails, if it's a SP network, let's say, millions of customers might be affected, okay? Depends on the size of the ISP anyway. So blast radius might be huge if core device goes down or if there is any problem, okay? So that's why future multi-area design migration can be easier. Option C is correct answer for this question. In OSPF version 2, which LSA types can cause partial SPF run? So we have actually many type of SPF. So let's just let me remind you, we have OSPF, open shortest spread first. We have CSPF, constraint-based SPF, which we use in traffic engineering with the RSVP. But of course, it's not the only place CSPF is used. Even when we have centralized controller, CSPF basically taking your requirement into an account. You want to have 50 MB LSP, you want to have disjoint paths, etc. Those requirements into an account CSPF takes. So it is not only on the routers, but distributed in the control plane on the routers, but on the centralized controller it can be utilized, and many other actually constraint-based SPF mechanism we have, different algorithms we have as well. So we have CSPF, as I said, OSPF, incremental SPF we have also partial SPF, we have full SPF, we have FSPF in basically fiber channel network we use FSPF. And so here partial SPF mean much less resource intensive task, okay, compared to full SPF. And we need to know this in OSPF basically type 3, 4 and 5. Type 3, 4 and 5 triggers partial SPF calculation, which mean what? Area 0, area 10. If something fails in area 0, area 10 routers will not have to run full SPF. They will just run partial SPF, which is much less CPU intensive. That was one of the reasons we have multi-area OSPF design, right? Because area 10 routers doesn't have this topology information of area 0 anyway. They cannot have full SPF. They don't need to run full SPF. Partial SPF mean update the metric information, or if there is a failure and if you lose some prefix information, remove this prefix information from the routing table. But doesn't have to run entire network graph and between each and every point what is the shortest path, etc. Right? So partial SPF is triggered by type 3 LSA, type 4 and type 5 LSA in OSPF version 2. Okay. Based on which design attributes number of maximum routers change in OSPF area? It depends on how many areas in the OSPF domain. Maximum number of routers in OSPF area should be around 50. We don't have this number. We talked about that, right? Depends on something, which is what? We talked about this question, very similar question, let's say. Depends on link stability, physical topology, number of links, hardware resources, rate of change. So we have links and how often those links are failure, etc. Depends on these guys, okay? Option C, which design attributes we say, depends on all these design attributes. Number of maximum rate routers inside the area, it can be 50 in different topology and different hardwares, different connection, physical connection type, very frequently failure links, failure nodes if you have in the network, and another topology, another totally different network, it can be 100, another network, 200, still OSPF, but totally different number you can have. Depends on the attributes, depends on the devices, hardware, a lot of, as we said here, a lot of things in your network. Number of routers inside the single area OSPF can change, guys. How many OSPF ABR routers should be placed in OSPF by keeping also redundancy in mind? So we will have ABR, how many of them we should have, basically. But we want also redundancy. Answer is almost always 2, guys. Okay, just say 2. Why? In design we have a motto. 2 is company, 3 is crowded. So 3 is crowded, 2 is company. 2 is good, 3 is crowded. Why you would need 3, 4, whatever, okay? Basically, you might need capacity also. Okay, you have maybe hub and spoke network or SPF, which you shouldn't probably, and 2,000, 5,000, whatever spoke site, and 2 hub routers capacity is not enough. So you put 4 routers, and let's say every 500 location is terminated on 1 hub routers, so on and so forth. Okay, this is what you would need, capacity requirement. Other than that, 2 is the answer of this, and in general. But why? Because redundancy they wanted. If they wouldn't say in the question redundancy, maybe 1 is enough. Some sites, this because it brings extra configuration, extra management, extra troubleshooting, operation, extra capex. You need to buy this. So nobody will give you free routers. If they give you, just send to me and we can use in the office, okay? So that's the point. But definitely 2 is company, 3 is crowded. 1 might be okay for the networks or on your network, some locations maybe, okay? Non-critical sites, critical sites, some of your location. But here the question says redundancy in mind. That's why answer is 2. Answer 21'i de lütfen bir 15-20 saniye, 30 saniye hatta göster ben konuşurken. Yani konuşmayı bitirmeden önce koyuyorsun bunları. So let's have a look at this question. What are the most important reasons of route summarization in OSPF? Choose 2 this time, I am saying. Route summarization, 2 most important reasons. In order to reduce the routing table size, so routers have to store and process less information, yes. Less number of, basically, prefixes, summarization, instead of /24/16. Let's say 10/24, 10 or 20 of them can be just summarized into 16/16, right? So much less number of information, conversions will be faster, troubleshooting will be easier, less amount of information you are dealing with, okay? So good, and memory resources will be used less as well, instead of having different entries /24 in the different FIB architecture anyway, like, I don't know, Patricia tree, Radix tree, all of them. So you have much less information, much less memory usage, okay, you will have. In order to increase the availability of the network, no, it's not related anyway with the availability there. Increase the security, no, okay. So in order to reduce, even if there is an impact on security, we are not doing for this purpose. We are doing for topology and less amount of reachability. In order to reduce impact of topology changes, so topology changes because will not be impacted anyway. Okay, if you can summarize, which means you have multi-area OSPF design. If you have multi-area OSPF design, between the areas, we don't have topology information. If something fails, if you add any new subnet, or if you change the metric of the new subnet, the impact will be much less in the another array, okay? That's the point. So that's why answer is A and D. What option E says? In order to provide optimal routing, no. When you summarize, we can have suboptimal routing. So we are increasing chance of suboptimal routing when we have summarize. When we have more specific information, okay, instead of 16, if you have /24, now we can have basically optimal routing, okay? That's the whole point. When we have summarization, we can have suboptimal routing. I'm not saying suboptimal routing is bad thing. Sometimes we do it purposely, intentionally. Traffic engineering, we will talk about it. But you can create suboptimal routing when you have summarization. Just we need to remember this.